back to my channel. So we're continuing on here in a sequence of RBF interpolation lectures where really I'm just taking you through the coding. Later on I'll talk to you about exact convergence rates and all those other things, but right now we're just going to talk about how to actually do it. So last time we took a look at a one-dimensional interpolation problem, and we used the Gaussian RBF, and we also used the Exponential Dot Product Kernel. Now what we'd like to do is we'd like to extend this to 2 and 3 dimensions and higher, because that's where scattered data interpolation is usually used. So in this case, I'm going to show you how to change our one-dimensional code to n-dimensional interpolation code, and we're going to take a look at a specific example for 2 dimensions where we interpolate the Franke function. So you'll notice that most of the changes I'm going to make happen to the display side. Actually, very little changes when it comes to the actual RBF code, like making the gram matrix and all these other things. That actually all happens very naturally. And so why don't we go ahead and jump into it. And what we're going to be doing is we're going to be trying to resolve this equation. So we have a collection of samples. We have x1, x2, x3, all the way up to xm, and that's an n-dimensional vector. And we have samples of a function that takes values on those vectors, and that's f of x1, f of x2, etc. We would like to be able to come up with an interpolant using an RBF, and that is this kxxi, or kxy, where kxy usually is something like a function that is radial. And so you're going to have, say, the absolute value of x minus y inside of another function, and that makes up your kernel. But we'll also look at this for a dot product kernel, because that's one of my personal favorites, to be honest. And yeah, so basically this interpolation scheme turns into this matrix equation, where the first row represents what happens when you put x1 into S, and then you take out the kernel functions as a row vector and the weights as a column vector. And then the second row is what happens when you evaluate x2, and you pull that out as a row vector and a column vector, and you arrange all these into a matrix. And on the right hand side is the values we're trying to match, and that is f of x1 all the way up to f of xm. And so that's what we're going to take a look at. Now we've already actually coded up the gram matrix portion of the code, and it's going to take very little in order to change this. And well, why don't we go ahead and take a look. So I did a little bit of legwork here, and I went ahead and I coded up Franke's function just because it's kind of tedious to do, and I didn't want to spend the whole lecture just coding this up. It's 4 different Gaussians, and you have one Gaussian that is positive. Yeah, it has a, it's 0.75 here. We have another Gaussian that is sort of in the normal direction, and then the last one ends up being minus sign. And if we go ahead and we plot this, and so I think that is this much here, then this is what you get. This is Franke's function. So Franke's function, it has a whole bunch of bumps in it. So it has a global maximum, it has a local maxima, and it has a saddle points, and it has a global minimum. And so it has a lot of bumps and wiggles, and that makes it kind of nice when you're trying to come up with some sort of function approximation scheme or interpolation scheme. It is a benchmark that is pretty commonly used. So this is what we're going to be working with. Okay, so if we go in here, what I just ran was this plotting code, and so I have the points that we were going to evaluate for the code itself, and so this is 1/100th steps from 0 to 1, but we don't want just one direction, we want 2 directions, and so we go ahead and we make this mesh grid out of these points here. And what that does is it gives us sort of this 2-dimensional array of x and y's, and if I go ahead and plug in x, you can see what you get. X is going to be constant down columns, and if I take a look at y, we're going to see that y ends up being constant along rows. And so when you take their collection together, and that is like this guy right here, then this x represents the x components of your data point, and this represents the y component. And so you just need to make sure you call both of them when you're making this vector. So now, so what I did is I made this mesh grid, and this gives us the points that we're going to evaluate at. But I need a vector to store all the values of the evaluation, and that's what the z is. Z, I made the zeros to match the size of x. This is a clever thing you can do in here, and basically it makes z the same size of x, just all zeros. We don't want it to stay zeros, so we go ahead and we plug it in. So for each I and j, we're going to plug in to z f of xij, yij, and this is a column vector. This column vector goes into f up here, and we extract the first component, this x1 corresponds to this guy, and we're going to extract the second component, x2, that corresponds to this guy, and that goes in Franke's function. So that all gets evaluated in, and then that's what, 100 times 100 points, and so that is in grand total 10,000 points that we just evaluated, I think. So let's see, size of z, just to see, 101 times 101, and yeah, so that's about 10,000. Okay, but it's pretty snappy. It's not too bad. Okay, so now we need to get down to the samples. The samples are going to be coming from this thing that we call a Halton sequence. The newest versions of MATLAB actually have a built-in Halton sequence command, and so this method here, this function I grabbed from MATLAB Central, which was shared by somebody, and he didn't put his name in the code, so I can't tell you who he was. But this is a now deprecated approach to it, but I forgot to install the package on my latest version of MATLAB, so I don't have it, but I had this sitting around, so I just used it. Halton sequence basically gives you a pseudo-random collection of points, and so it's really nice if you want to just fill out some sort of interval. By default, it fills out, say, 0, 1 to the nth power, and so here 2 would represent 2, so it fills out 0, 1 by 0, 1. And if you wanted to scale it to fit some other region, you just multiply and shift however you need. And so a Halton sequence asks you how many numbers you want and what dimension they should be. And if I run this code, then it gives me row vectors as my data points. So this is a two-dimensional row vector, and I don't want that. I like working with column vectors, and so I take the transpose, and that's here. Okay. Technically, I should probably take the non-conjugate transpose, because prime is technically the conjugate transpose, but these are all real values anyway, so it doesn't matter. Okay, so now my samples, I just make a vector the same size as my samples in order to catch all the values of y. So this is where the values that we're going to be using for our interpolation are actually coming from, is this z samples. The other bit was just so that we could see what we're getting, but the approximation scheme doesn't see this at all. So now I basically throw these samples in here, and since each of these are columns, I select the entire column using this colon here, and that is sample I, and I plug it in to F. And so H was my Halton sequence, and it's going into F in order to give me my samples here. All right, pretty easy. And then here I use the plot3 command in order to see where my interpolation points actually live. So let's go ahead and take a look and see what we have so far. Okay, so here's my figure. It's the same thing we saw before, but now it's peppered with our sample points. And it looks like they're kind of all over. And yeah, that works for me. And we'll see how good of an interpolation we actually get by using this method. Okay, so now let's move on. So this is where we stopped, and this is everything I filled out before. Now, I didn't want to take forever in setting that up, and hopefully I explained it well enough in order to get you through it. But now let's see what we need to change from the kernel side, and this is the really important bits. So here, norm x minus y for two column vectors x and y, this is going to perform exactly the same as it did before. That doesn't need to change. Mu, we might have to adjust mu later. We'll see. It just depends on the samples and how good of an approximation we get. 0.75 seems really, really big for a region that is 0, 1 by 0, 1, but we'll see how it does. And ditto for the exponential dot product kernel. It's commented out here because we want to start with RBF interpolation, but we'll make a comparison later. Okay. So here we have a grand matrix, and is going by zeros the length of t samples. That's not what we're using anymore. What we have is we have how many samples, and so we're going to go ahead and make that change. We could have done this in the one-dimensional case, but we're just keeping things pretty easy. And so these two loops go through all of the gram matrix entries, so that just needs to be adjusted here and here. And now for these guys, these are going to be our halting points. So we have h colon comma I and h colon comma j, and these each get put into K, and then that is thrown into this gram matrix. All right, this is still the slow way of doing the code, and in the future I'll show you how to do it faster. It gets to be bottlenecked as we go higher and higher dimensions, and we need denser and denser collection of points, and that's gonna make the code choke really bad. But there's ways to get around it, and I'll show you later. All right, sampled output. We don't need this anymore. We actually have our samples up here. That was the Z samples guy up here. So now let's see the weights. Well, it's the same inverse equation, but now we just change the variable Z samples. And Z, well, Z was our surface plot up here, if you saw that up here. And so we're going to need to change this Z to be something else. And so we'll say Z approximation. And so I'll put that in here. There it goes. And in here, it isn't T evaluate anymore. We're going to be, yeah, so this needs to be size of X. So, because we're filling out the entire surface, right? So that needs to be to match the two-dimensional case. And so now we're going to have IJ here, and let's try to make us, let's see, let's try to copy what we did up here for evaluating for our surfacing. So I'll take that, I'll put this here, and put end there. So we caught that. Okay, all I'm doing is just changing this plot. This actually has nothing to do with the kernel interpolation, but if we want to see the result, we need to fix this up. So the sum stuff is still the same. So sum starting at 0, and then we add each one of these one at a time to this variable. So we say sum is equal to sum again plus this extra bit, and then that basically works out some sort of series. And here, of course, instead of t evaluate, we're going to be putting in xij comma yij, and, or not comma, but semicolon. And for samples, this is going to be our halting points, h, and colon comma j. We shouldn't be using that anymore. Let's change the internal variable here to be ii, because this guy was j, and we don't want confusion. So this changes to ii, and there we go. And now I and j are now the indexes that run through our little square, and ii is now the index that runs through our weights and our number of samples. And so, let's see, and this should be changed to how many samples, I think. Yeah, how many samples. Okay, there we go. And now instead of figure, we're going to do a surface plot. So surf, and then we're going to have x, y, and then z approximation. And then, well, we don't want hold, but maybe we should have another figure. And here we're going to have another figure where we are comparing our approximations. So we're going to have, say, surf x comma y comma, we're going to take the absolute value of z minus z approximation, and there we go. So we'll go ahead and run this and see what we get. Okay, so to start, we see that we have this same function we had before. This is Franke's function, and these were our samples. So just a quick reminder. Now let's go take a look at the second figure. And so this is our approximation. It's kind of muddy. It kind of has the right shape. We have a few peaks. We have the maximum there, and we have local maxima there, and we have a minima there, but it's not working out too well. And you can't really tell if this is supposed to be bigger than this or what's going on. And this seems to drop down really far, really fast. And so we'd like to get a better approximation of what's going on. So, and we can take a look at our actual approximation and error. And let me go ahead and get that up. And so now you can see this is the error. The error is actually fairly good. If I take a look inside here, it's 1 times 10 to the minus 3. So it's actually pretty close, except out here it gets kind of bad. There's not a whole lot we can do if we don't have any sample points near those guys, and we can generally only trust this sort of scattered data approximation in sort of the interior where we have a cluster of points. And so, but it looks like when on here, this is like 5 times 10 to the minus 4. That is actually excellent. But let's see if we can get a little bit better and take down these big towers that we have on the outside. And I think that's going to come down to adjusting our mu. So getting down to where we define the kernel. There we go. Now let's take this down to, I don't know, 0.1. Let's see if that improves things. So if I go ahead and plot it, let's see what we get. All right, so again, you see the figure for the Franke's function, and let me try this again. There you go. All right, so this is the approximation again. There's still a lot of really bad bits, like especially out here. And let's take a look at the error real quick. And so if I go ahead and evaluate this guy, on the inside, it's actually gotten a lot better. It's 2 to the times 10 to the minus 4 here. And that is maybe even times 10 to the minus 5. My eyes are it's getting hard to read that tiny text. But yeah, so that's an excellent on the inside. We're still having something kind of crazy going on over here where it's like 0.75 error. And maybe we can do better. I don't know. It's getting iffy if we can actually do better than that, but why don't we go ahead and try? So one thing I'm noticing is we have 100 samples. So, figure that's like 10 samples per axis. I mean, these are Halton sequences, so they're sort of randomly distributed, so you can't really trust this. So, but they're at best, they're 0.1 away from each other, in one direction. And so I'm going to try to have what I have here. And so take it to 1/20th. And now let's see what happens. Okay, so our approximation, yeah, that's much better. This is our approximation. And I am proud to tell you that I have to tell you it's my approximation because the approximation is really, really good. And yeah, it seems we got rid of those weird towers on the edge that seem to be off. And if we go ahead and take a look at the error, the reason why I have to keep evaluating that is because I only have 2 windows in OBS, so I have to rerun this. But okay, so this is the error, and you notice that the worst error we have is 0.07, so that's 7/100ths, and that's not bad for what we have going on here. And here, I mean, that's like what 1, 2, 3, 4, so that's 1 times 10 to the minus 5. That's an excellent error on the inside. And so yeah, this is pretty good error, and this is sort of probably the best we can get for this collection of points. So there's a few ways you can still try to improve this. I can take this up to say 200 and try to see what happens. And boom. So there we go. That is our approximation. It seems okay. Maybe we have a little wonkiness going out here on the corner. I'm not sure. But yeah, looks about right. And if I take a look at the error, It's pretty good. It did get bad again with one of these towers here, and yeah, it's probably because, again, we need to adjust our kernel width. But otherwise, yeah, it's like 10 to the minus 5, 10 to the minus 5. On the interior, we're doing fantastic, and that's really the only place you can trust this approximation anyway. On the boundaries, you would have trouble one way or the other. Okay, so that's good. So now, why don't we see, I'm just going to uncomment this, and let's see what happens when we use the RBF kernel. Sorry, the Exponential Dot Product Kernel. And so, if I go ahead and run this, let's see. So, it does okay. We are still getting a lot of those same peaks and valleys. It doesn't look quite as good, but again, we were using the RBF, Gaussian RBF, and we were approximating Gaussians. So, I mean, you know, maybe it wasn't a surprise that worked out as well as it did. But this one still seems to be doing pretty good. It does have the towers on the corners that are kind of a problem. And, yeah, but, oops, didn't mean that. So why don't we go ahead and take a look at the actual error. And that's the only real way to get a sense for what's going on. So again, yeah, the towers on the sides, but 0.01, and you know, so as a first try at doing this, that's not a bad error. It might be that this function just doesn't align well with what we have, but I mean, honestly, it's not bad. So let's see if we can make it better. So I'm going to change this to 2, and again, we're still using the 200 sample points. So it could be that, you know, maybe we'll even do better with less. But let's see what we got. Okay, so I changed it. I actually increased the quote kernel width and trying to choke down some large values that could be coming out of the exponential. It seems to do okay. And if we take a look at the error, here, no, we did worse. So it's 0.1, etc. I love these blobby looking things though. But yeah, so but it gets decent approximation if you go the right way. And so let's see what we get if I use just 100 points. Oops. Forgot to close Windows. All right, there you go. Try it again. Okay, so with 100 points, looks like we're back to doing okay. The colors don't really match up with what we usually expect, but I mean, that's fine. Let's go ahead and take a look at the error. And the error improved quite a lot. So we're down to 3 100ths, 3 100ths, etc. And so a little bit of parameter tuning, it looks like, could help us there. The Gaussian RBF actually comes with a good convergence rate estimates for the function itself, whereas the exponential dot product kernel doesn't. Dot product kernels don't have nice convergence rates that have been established. We generally suspect that they're good, but there's no theorems that really tie it all together. All the tools that work with the Gaussian RBFs and other RBFs really comes down to some nice Fourier tricks that you can do by looking at the Fourier transforms and doing some work on that side. And they end up being sort of like Paley-Wiener type spaces. And actually, some of them actually work out to be like straight up Sobolev spaces, but that's neither here nor there, not at this point. So in any case, what we've done is we've changed the code to work for 2 dimensions. And now the next step is to figure out other kinds of kernels that we can try to do interpolation with. What I'd like to do is I'd like to tell you about the Wendland RBF, and I'd also like to tell you about how to code this up faster, and that's probably going to be the next thing to do. And then also Fasthauer and McCourt back in 2012 published a nice paper that tells you how you can handle really, really close together points for, say, the Gaussian RBF. And so he has a method of breaking down the Gaussian into Hermite-like functions, and then he can analytically invert that matrix. And so, yeah, it's anyway, yeah. So those are the things I would like to do, and over the next couple weeks, I'll record a bunch of really short videos and put those out, or at least short for me to put together. And yeah, it'll be a lot of fun. But don't worry, we're still going to talk about DMD. I have another video I'm editing right now. I just wanted to try to see if I can crank out a couple of quick videos here, and yeah. So if you want to see more, please like, subscribe, comment, and yeah, I'll see you next time. Here's my Instagram.